So what I'll be presenting on is a project from a few years back that we're still working on today. And these were field trials of microbially-induced desaturation, looking at the application for earthquake liquefaction mitigation. We performed these trials in Portland. And before I begin, I just have to acknowledge all the collaborators on this project. From Portland State University, my colleague Arash, and our graduate students Kayla and Melissa, as well as our collaborators from University of Texas, Austin, Arizona State University, and Condon Johnson and Associates, and Yume Wong as well. So we're all fairly familiar with the hazard of earthquake liquefaction, where we have loose, saturated soils that lose their strength during earthquake shaking, causing damage to infrastructure. But what I want to highlight from this photo here is this photo here, and I believe that this was after the Chile Male earthquake. Damage at a fuel tank farm caused spills and burning of the fuel, creating quite a messy situation on top of the earthquake itself. And this is something that we're concerned about in Portland. So when we look at the liquefaction hazard in Portland, we have two primary seismic sources that we're looking at. There's the Cascadia subduction zone, up to magnitude 9 earthquake, and in Portland we're about 100 kilometers from the source. In Portland itself, there's the Portland Hills Fault, a shallow crustal fault that's also a concern for the seismic hazard. When we look at liquefaction within Portland, we're primarily concerned about these young alluvial soils along the Columbia River and then the Willamette River as well. You can see on this liquefaction hazard map here that they're bright red by the Oregon Department of Geology. So like I said, these are young alluvial soils associated with these rivers. And along the Willamette River there and into northwest Portland is what we call the critical energy infrastructure hub. It's a big fuel tank farm that stretches about 9 kilometers along the Willamette River. Young, loose, river deposited soils and also dredged soils as well underlie many of these tanks. And this is really our concern, that during an earthquake, these soils will liquefy, damage the tanks, causing spills, and then also a loss of that resource, so that we won't have that fuel to then recover following the earthquake. And the stat here is that 90% of Oregon's liquid fuel is handled through the CEI hub, and actually 100% of the jet fuel for the Portland airport goes through the CEI hub. So this is really a critical lifeline that there's quite a bit of concern of its performance during an earthquake, particularly the geotechnical performance. Along the Willamette River and underneath the CEI hub is a lot of silty, fine-grained soils, and there's not a lot of mitigation methods that we can apply underneath these fuel tanks. They tend to be old, maybe a little bit fragile, and so we can't use really invasive soil improvement methods. One that you would often go to for silt soils would be deep soil mixing in a grid pattern. And as you can see in the video there, quite invasive for soils that are beneath these fuel tanks. And then on top of that, there's just not a lot of economic solutions that would then compel the owner-operators to improve these soils. So we're kind of doubly hit when it comes to addressing the seismic hazard at the CEI hub. There's these fine silty soils that are difficult to mitigate in the first place, and then if you can, it's also very expensive. So looking at a potential different approach to mitigating the earthquake hazard at the CEI hub, there's microbially-induced desaturation, or MID. And one of the advantages of this method is that it can potentially be used beneath existing infrastructure by introducing a treatment solution to the subsurface, and then the seepage of the groundwater and the treatment solution can go underneath the existing infrastructure. So in that sense, it may be, or it is non-invasive. That treatment solution, it stimulates native denitrifying microbes. They perform a denitrification reaction that results in mostly nitrogen gas, but also potentially carbon dioxide gas as well. And then that biogas displaces the pore water, desaturating the soil. This figure on your right here shows comes from the research at Arizona State University, and it's showing 2 sand grains with the remnants of one of these MID bubbles that formed with the calcite precipitation that happens later on if you push forward that reaction, the calcite precipitation between those 2 bubbles, or between the 2 grains, but the remnant of the air bubble there is the takeaway. And one advantage that we see for microbially-induced desaturation in these fine-grained soils is that we have small pore spaces, making it more difficult for those air bubbles to migrate out and potentially improving the longevity of MID for fine-grained soils, at least compared to coarse-grained soils like sands. The method's been looked at, or has been pioneered by Ed Kavazanjian and Leon von Passen at Arizona State University, and they've spent a lot of time on these small-scale and medium-scale lab tests, like seepage columns, medium-scale seepage tanks, doing some numerical modeling as well of the transport and reaction. And then there's multiple field tests that they've done, one in Toronto, ours in Portland, and I don't know whether one ever got off the ground here in Richmond, but if you know anything about that, I'd be happy to talk about it. So when we look at the way that MID, or at least soil desaturation, addresses the liquefaction hazard, by introducing a small amount of gas into the soil's pore fluid, we increase the compressibility of that pore fluid. So that when we have seismic loading, there's a drastic reduction in excess pore water pressure due to that compressible fluid. These are the results from Hay et al. Of some shake table tests on fully saturated here on the left, and then saturation 95%, 80% as you move along. And you can compare with the excess pore water pressure plotted on the y-axis. For fully saturated soils, we're mobilizing up to, at the prototype or the lab scale, about 45 centimeters in excess head. And then that becomes suppressed and reduced quite markedly with these reductions in saturation, to the point where we see very little excess pore water pressure build up at a saturation ratio of 80%. O'Donnell et al. Out of ASU, they tested this a little bit more directly in the lab with direct sample shear tests, and could then characterize the gain in cyclic strength with the reduction in saturation. So plotting up data, cycles to liquefaction on the x-axis and cyclic shear ratio on the y-axis, we see that fully saturated sands at their cyclic strength or cyclic resistance lies below the saturation of 99 and 97% from these data. So with a small reduction in saturation, they've shown in the lab that we can get quite a remarkable increase in the cyclic strength of these soils and a resistance to liquefaction. So we wanted to test this at the field scale and see how this would perform outside of the lab in the field under field conditions. So in the summer of 2019, we performed 2 field trials in Portland, one at what's called the Sunderland site here along the Columbia River. And this site, what's notable about it is that it's near the Portland airport. So there's quite a seismic challenge with the airport itself. So by testing these soils directly, we could also inform some of the engineering going on at the airport. And this site, we had access to it from the Portland Bureau of Transportation. The second site is just at the top corner of the critical energy infrastructure hub, called the Harborton site, and we gained access to the site from Portland General Electric. So the objectives of our field trial were to look at MID at the field scale, and then also how it's performing in these silty soils, since most of the lab work had been done primarily on sands. We also wanted to evaluate its longevity under field conditions. I mean, what good is this soil ground improvement method if it can't last the lifetime of the infrastructure that we're looking to protect? And then we also wanted to study its effectiveness for liquefaction mitigation. And so that last point there, I'll touch on that at the end of the presentation. We investigated that with the use of the T-Rex mobile shaker truck from University of Texas Austin. And these were the first field trials of MID for liquefaction mitigation in the US. So what I'll go through today as I go through these field trials, I'll start by just presenting the subsurface conditions at our field trial sites, at the Sunderland and Harborton sites. I'll go through the way that we ran these field trials with the MID treatment and solution application, we'll go through the data during the first 100 days to look at our monitoring data and see just how successfully we did manage to desaturate the site. And then now that we're we're 3.5 years out, we can start to look at long-term monitoring at the site and start to understand the trends that we're seeing in the desaturation. And then finally, I'll talk about that mobile shaker truck testing that we performed at the Sunderland site. So, Sunderland site, subsurface conditions. The site near the Columbia River is on floodplain deposits from the Columbia River. These are primarily fine-grained with an average plasticity index of about 14. And using the Brain-Sanchio approach to liquefaction susceptibility, they classify, the range of classification ranged from moderately susceptible to liquefaction. We have the cone profile here on the left, as well as outlining the soils that we targeted for the MID treatment. So soft, fine-grained soils at this field trial site. At the Harborton site, like I said, is underlain by river deposits and dredged fill. And we see a lot of interbedding at this site between plastic and non-plastic silts. With the low-plasticity silts in the interbedding, they have a plasticity index of about 13. And similar to the Sunderland site, they classified as moderately susceptible to liquefaction. We did a smaller treatment zone at this site. It was just, it was 5 feet of the targeted treatment zone. And you can see in the cone profile that there is some more interbedding at the site. And there's a little bit more variability at this site as well, interestingly. So looking at the way that we perform these field trials with the treatment solution itself and then also applying it into the subsurface. The treatment solution is an aqueous solution of calcium nitrate and calcium acetate at a 0.05 moles per liter concentration, and about a 1-to-1 molar ratio between the acetate and the nitrate. You can also sort of control the rate of reaction of the denitrification reaction by adding Miracle-Gro and Epsom salts to the solution. So you can kind of like dial it in that way, where if you think that the reaction is occurring too fast, you stop adding Miracle-Gro, but if you want to really boost up those microbes, then you add the Miracle-Gro. Anyways. And then this is just going through the reaction of the acetate and the nitrate in solution. So they go through the denitrification reaction, and the nitrogen gas is the primary product that we're after here. If the solution can continue on, like if there's additional calcium in the solution, then what happens is the next part of the reaction, which you may have, I think that you've had presenters on this before, but that's where you get the calcite precipitation and the cementing of the sand grains together, the soil particles together. And then if you go on further from that, you get carbon dioxide gas. With the concentrations in solution that we had, we were targeting this part of the reaction as opposed to continuing on to the calcite precipitation. So our primary products were biogas with a little bit of, or I shouldn't say a little bit, but we also got biomass along with it, which is just a byproduct of these reactions. In order to apply the treatment solution at both sites, we had a central injection well that we pumped the treatment solution through with an inline pump, and then extraction wells at about a 3.5 meter radius around that injection well. We also used gravity feed at night, which it wasn't as effective as the inline pump to inject the treatment solution into the subsurface. This is the targeted zone for soil treatment. We kind of sketched it out around those extraction wells, assuming that the extraction wells would be able to capture a lot of the groundwater within this zone. But we'll get into that later, that in fact the treatment zone appeared to be quite a bit larger. So at the extraction wells, we extracted water from them in order to kind of try and keep a closed system so that we could mix the solution into the extracted water and re-inject it into the subsurface. As well, we wanted to encourage that seepage of groundwater throughout the targeted soils. But we also didn't want to draw down those wells so much that then we were potentially inducing desaturation through well drawdown. So we did have a control system of submersible pumps and some float switches in order to keep the water level from drawing down into the treatment zone itself. This is the setup at the Sunderland site. We have the central injection well in the middle and then the 4 extraction wells around it. There's also this point here, which is a in situ sensor array. So we have a vertical array of sensors between the injection well and the extraction well. And then there's also a seismic array here for taking crosshole seismic measurements as a means of monitoring the progress at the site as well. At the Sunderland site, we screen the wells from 1.5 to 6.1 meters depth, so about 15 feet, a pretty sizable targeted zone there. And that's in contrast to the Harborton site where we had a smaller treatment zone. It was about 5 feet, a 5-foot interval, or 3 meters to 4.6 meter depth. But very similar setup at the Harborton site with the injection well, extraction well, and then the sensor array between an extraction and injection well. We did not have a seismic array at the Harborton site, and actually we didn't have long-term access to the Harborton site either. They were going through construction at the site just a few months after we finished the field trials. So we injected the treatment solution for about 4 weeks at each site. And at both sites, we were able to displace about 60% of the pore water within that volume of treated soil at each site. So these are plots just showing the treatment injection volume on the y-axis, and then the time from the start of treatment on the x-axis. At the Sunderland site, this is the site that we started treatment off at. So we had a little bit of time to kind of get our system going and to start to manage the well clogging and the biomass. But then once we kind of got into the routine and were able to troubleshoot things, the injection rate became a lot more steady. On the right, at the Harborton site, we had a similar steady rate of injection. And like I said, by the time we finished both field trials, we had injected about 60% of the pore water volume within that targeted treatment zone. These plots are just showing some of the injection rates. So at the Sunderland site, it was about 10 liters per minute when we were actively injecting the treatment solution into the subsurface. And we could measure this with some instrumentation, but mostly it was with analog readings off of an inline flow meter. And then at the Harborton site, we had lower injection rates just because we had about a third of the size of the well screen through which to inject at the Harborton site. But the point that I want to make here is that one of the things that we were concerned about with MID in these fine-grained soils is that we wouldn't have the permeability in order to transport the treatment solution throughout the targeted treatment zone. And you can kind of turn the dials on the design of the treatment solution and then also the injection rates so that you can have the reaction occurring further from the injection zone if you do have those fine-grained soils, so that you're not just having most of the reaction occurring around the injection well. All right, so that was the way that we applied the treatment solution within these soils. So now looking at the data that came out of this. The monitoring at both sites was set up to primarily observe changes in saturation ratio, but we also wanted to look at the migration of the treatment solution and how it was spreading throughout the treatment zone, and looking to see whether we actually are observing that MID reaction happening in the subsurface. So that we can see all of this happening together and therefore be confident that those changes in saturation that we're measuring did come from MID. Our instrumentation system, we had several approaches to instrumentation. First, our CTD divers that we had in these tanks that we held the injection solution and the extracted groundwater in. And those could just give us measurements of the volume that we were injecting into the subsurface and then also extracting as well. They measured electrical conductivity, and electrical conductivity became a really nice indicator of the MID treatment solution progress, because most of the treatment solution was dissolved substrates. So we start with a high electrical conductivity, and then as the reaction progresses, those substrates are consumed and the electrical conductivity of the groundwater or the treatment solution reduces. we had TEROS 12 in situ sensors, that sensor array between the injection well and one of the extraction wells. Those sensors, they're inserted into the side of an augured borehole at the site, and they measure bulk electrical conductivity and water content within the soils there. The last instrumentation data collection aspect that we had is this sensor array, which was only at the Sunderland site. And this was for the T-Rex mobile shaker truck testing. It was also for regular monitoring of the seismic velocities at the site. So we had seismic wave velocities through crosshole measurements from the sensor array. We also performed direct push crosshole seismic initially before the testing took place. And the sensor array can also measure cyclic induced pore water pressure from the mobile shaker truck, and we can compare that for before testing and then after the treatment was performed. So looking at these TEROS 12 sensors, as I already explained, they measure electrical conductivity, and we can also interpret a water content of the soil from them. The sensor array, we placed it at the Sunderland site at 6 different depths between the injection well and the extraction well. And one of the measurements that they take are electrical capacitance, which then relates to the moisture content of the soils. And we could, by assuming whether the soil was already initially saturated, we could take those changes in moisture content and relate them to a change in saturation. So reduction in moisture content, reduction in saturation. These are showing the data from both sites, the the Sunderland site here on the left and the Harborton site on the right. We have saturation ratio on the y-axis and time since started treatment on the x-axis. So this is just zooming in on our time of treatment and then for about the 100 days following the treatment. And we can see that we had, at least interpreted by these TEROS sensors, we can see a reduction in the saturation that started soon after that treatment solution was injected into the subsurface. We could also confirm these measurements by looking at Shelby tube samples of soil and measuring the saturation on those soil samples as well. And we see generally good agreement between the Shelby tubes and these TEROS data as well. So this was to us a good indication, although not the only indication, that we had successfully reduced the saturation in these treated soils. The other way to look at the saturation was with pressure wave velocity. And so soils with 100% saturation, a pressure wave or compression wave will travel through the pore water and at the speed of water. And so we see that for soils that are nearly fully saturated or fully saturated, the pressure wave velocity, we expect it to be about 1,600, 1,500 meters per second. Then when we start to introduce a little bit of air into the water, we see a marked decrease in the pressure wave velocity. And the rule of thumb that we used was that for saturations less than about 98.5%, we expect the pressure wave velocity to drop to about 400 meters per second. So seeing that drop or measuring that drop would be an indication that we had crossed that threshold saturation value and lowered it below 98.5%. The pressure wave velocity, we could measure it regularly with that crosshole array that we also used for T-Rex testing. This picture here is our student, Kayla, performing that crosshole seismic array testing. The source is an instrumented hammer to record the time of the source, and then the instrumentation or the geophones in the subsurface shown here, those record the time that the wave arrives at the geophone. So we can look at the different arrival times between the two geophones at each depth, and then average the distance over that arrival time to get the P wave velocity between those geophones. We could also measure VP with seismic cone penetration testing, which was really useful for probing different areas of the treatment zone and seeing the P wave velocity in different areas as opposed to the fixed array here. These are some examples of the crosshole traces that we got for the geophones at 2.5 meters below the ground surface. The top one is, I think that this one, 5 days before the start of treatment. So yeah, these traces or these time series before treatment when we expect the soil to be fully saturated, and we see a nice arrival of the P wave at both the close and the far geophone. On the bottom, this is 43 days after the start of treatment, so well into treatment, and we can see that we've had compression wave attenuation. We don't get that nice trace of the compression waves. The first geophone, and then we can just pick out the arrival at the second geophone here. And there's also quite a big difference in the arrival times between the start of treatment and 43 days into treatment. So, this is showing the results of those crosshole measurements at the Sunderland site. So P wave velocity on the y-axis and time from start of treatment on the x-axis. The two deepest geophones at 2.55 and 4.55 meters, those with the initial measurements, we see that increase or that high P wave velocity value of about 1,500 meters per second. And then about 10 days into treatment, the drop in P wave velocity to about 400 meters per second. So that is a strong indication that we did also have a reduction in saturation at these depths. The 1.85 meter geophone looks like the soils may not have been quite over 99.5% saturated initially, but at that geophone and the geophone above it, we do see a continued reduction in P wave velocity, indicating that saturation at all of these geophone depths remains below 98.5 or was below 98.5% during and for these about 80 days following treatment. So this test was another indication that we had successfully reduced the saturation within these treated soils. And then this, going back to that relationship between P wave velocity and saturation from the O'Donnell data, we could pair our TEROS data with that crosshole data, like for similar days that they were measured. There's a little bit of an adjustment in there to just account for different seepage distances. But I thought that this was quite interesting in that our data, when we pair them, saturation and P wave velocity, we see a similar trend in relationship between saturation and P wave velocity that's measured in the lab and also supported by theoretical relationships as well. I have lab data plotted on here as well to compare. So another indication that the TEROS data and the crosshole velocity data are supporting each other, and more evidence that the site was successfully desaturated. We performed cone penetration testing. ConeTech helped us out with this, both before treatment at the site, but then after as well. And like I said, with that post-treatment, we could probe different points in the treatment zone to see if there was any variability, like if we did desaturate at the points that we tested, not just at the points that we had instrumented. So on the left is the Sunderland site, on the right is the Harborton site. We do have more data from the Sunderland site. We have this initial profile from direct push crosshole. This is the initial profile pre-treatment from CPT testing. And then these dashed lines to the left, the blue ones are points that we measured for P wave velocity within the treatment zone. And then interestingly, this point here, the black dashed, that was a point I think about 3 meters outside the treatment zone. And we see that the treatment solution did actually migrate beyond the treatment zone, the targeted treatment zone, and reduce saturation out there as well. So, and then we see something similar at the Harborton site, where we see that decrease in P wave velocity profiles at different points within the treatment zone, and then also outside of it as well, at least compared to the initial pre-treatment profiles. So, lastly, after treatment, I think it was about 2 or 3 months after treatment, we went out to the site and took some Shelby tube samples. And then we took them to a lab that could x-ray them. And we thought that this was quite interesting, that with the pre-treatment Shelby tube sample, it looks like a nice intact soil sample. And then on the right, this is a post-treatment where you can see that modeling throughout the sample, indicating that we did get pockets of that biogas accumulating in the soil. And it looks pretty similar to just kind of a bench scale demonstration experiment that we did of mixing the soil with the treatment solution and leaving it on the lab bench and looking at the air pockets that formed. So, all right, so we saw from those field trials that we we believe that we successfully desaturated both of these sites. Different stratigraphies, but both fine-grained soil sites that we saw evidence of desaturation from microbially-induced desaturation treatment. Now we're 3.5 years out, so we can start to look at what's happening seasonally and over years at this site. We do have long-term access to the site at Sunderland, and it's proven to be pretty interesting. So the picture on the left is the way that we worked at the site and the conditions it was generally under. Nice and dry. You can see our instrumentation here. It's grown over. Actually, interestingly, the reason we have access to this site is this is classified as a wetland, so they can't develop on it, and which is also why they don't cut the grass around it. Anyways. This is the site here. This would be in the winter months in Portland where it's flooding, and there's over 12 inches of water right over top of that sensor array where we're taking the crosshole measurements. And this happens seasonally at the site. So when we start to look at those Teros data, as shown here at the saturation, and then the water level that we measure at the site whenever our student Kayla goes out there. And also these points here are when we saw or measured the groundwater flooding. I also believe that there was flooding in here in the winter, but I don't think we took measurements to then support that. But we can see, especially with these deeper Teros sensors, the ones 3.66 meters and below, we see very little response to the groundwater flooding at the site or to those fluctuations in the water level. The shallowest sensor at 0.91 meters, which was above the treated soils and generally is above the water table, we do see that this one responds to the dry season here and then also the seasonal flooding, and that those soils do go back to about 100% saturation. Then with the next two sensors at 1.83 and 2.74 meters, we may see a little bit of response in the dry season when the groundwater table is at its lowest, but we don't see them going back to that 100% saturation or increased saturation compared to the saturations that we achieved in the months post-treatment. So this to us gives us a little bit of confidence that at least it looks like this microbially-induced desaturation can sustain water table fluctuations and as well as site flooding as well, at least if you're far enough below or at the level of water table fluctuation. The pressure wave velocities from the crosshole measurements, those have also stayed reasonably low, indicating that our saturation has sustained below about 98.5% at these crosshole measurements too. All right, so the cyclic testing that we performed at the site. So we did pre-treatment testing at the site so we could understand the excess pore water pressure behavior and generation of these soils when they're fully saturated before treatment. And then we treated the soils throughout most of August and performed the post-treatment testing in September of that year. And we wanted to compare the excess pore water pressure response due to the cyclic testing of the untreated and the treated soils. So the mobile shaker truck is called T-Rex, and the testing is performed by putting this base plate in contact with the ground surface and then transmitting the ground motion through that base plate. And the hydraulic system actually lifts the wheels up off the ground, and so it's just the base plate that's imparting that motion into the soil. And then the instrumentation below the base plate measures strains and the generation of pore water pressure. So this is the instrumentation array, the same one that we use for the crosshole measurements, but we have finite elements made up by the geophones or the accelerometers, and so to estimate the strains that are being felt then at these pore water pressure transducers to look at the excess pore water pressure generated. So this exemplifies what we saw at the site, and we actually had some challenges with the cyclic testing, and so we do need to investigate it further. But what we're looking at here is the time series of shaking, the time of shaking, and then the excess pore water pressure that's measured at the pore water pressure elements. At this case, I think they're at about 2.5 meters depth. So we're comparing the untreated soil in the blue with the treated soil in the orange, and looking at the excess pore water pressures that developed after shaking. we do see a reduction due to the MID treatment from about 10% RU pre-treatment to 6% post-treatment. But one of the things that we're challenged with here is that the shear strains were pretty small. They ended up being about, well, yeah, shown here about 0.127 or 0.13% shear strain. And when we look at the excess pore water or cyclically induced excess pore water pressure behavior for a lot of the soils, for those same soils and then similar soils in the Pacific Northwest, we really generally see that the excess pore water pressures take off at larger strains than what we could induce in the field, just because with shaking at the ground surface, there's attenuation of those strains with depth, and to our treated depths and instrumented depths, we just couldn't get quite enough strain. So the green symbols here are results of the T-Rex testing and then some RCTS testing that took place on those same soils at University of Texas. The red and the purple symbols are from direct simple shear testing we performed at our lab. And so we believe, or our hypothesis of this is that we need to really understand the impact of MID on excess pore water pressure behavior and generation, we need to be looking at larger strains than what we were able to mobilize in the field. All right, so wrapping this up, we performed these 2 field trials of microbially-induced desaturation at the field scale in silty soils. And these 2 sites, they had distinct stratigraphies to them. One was a nice kind of homogeneous floodplain deposit, and the other was an interlayered, non-plastic, low-plasticity silt deposit. But at both sites, despite these distinct stratigraphies in the fine-grained soils, we believe we successfully desaturated them with MID, as indicated by our pressure wave velocity measurements, direct soil sampling, and then also these moisture sensors as well. And then a note here that the rate of chemical reaction can be designed to be compatible with permeation rates, which would be the concern in these fine-grained silty soils. Looking at the longevity of MID under these field conditions, we have about 3.5 years of pressure wave velocity, terosensor data, and physical sampling. And they all indicate that we achieved the reduction in saturation and that it has sustained for about these 3.5 years. And that they appear to, in the treated soils at least, appear to withstand site flooding that annually occurs at this site, and also water table fluctuations. And then looking at the effectiveness of MID for liquefaction mitigation, we did see some reduction in pore water pressure between the pre and the post-treatment shaking with the T-Rex cyclic testing, but we consider it inconclusive at this point. So thinking about what we're doing next, well, we want to do more cyclic testing to better understand MID and its effect on liquefaction hazard through either field and or in lab testing as well, looking at different saturation levels and strain levels. As well, even if we understand that this reduction in saturation can reduce excess pore water pressure, is it still reducing the hazard that we may face with these soils? Like, is it reducing potential settlement or lateral spreading just because we've desaturated these soils? And then, of course, we have this site, we have long-term access to it, so continued long-term monitoring at the site so we can look at the longevity of MID in these soils over time. Again, acknowledging the many collaborators on this and the partners that allowed us to perform this field trial, and also some references to point you to if you would like to read up on it a bit more. I'll actually point you to this one here, which was done by the team at ASU as well as Condon Johnson, and they did a kind of an economic analysis of MID versus, I think it was injection grouting for sand soils to compare the costs of the different methods. So yeah, that's an interesting case study to look at there. And with that, I'm happy to take any questions.